Okay, so I will just give a brief introduction on millimeter interferometry. I will basically I will touch two different things. So the basic principle of interferometry, the instrument and the principle themselves, and then I will talk a little bit about the effects of the atmosphere. I will not talk about calibration because the way ALMA is working is ALMA Observatory is taking care of everything about the calibration and just give you the PI and the user just give you almost perfect data. So, but if you have any question on calibration and issues like this, then we can discuss maybe after if you want, but I will not touch in the talk. So first I will start with the basic principles of interferometry. And it's all about angular resolution. So we are interested in astronomical objects. So usually they are very far and usually they are small. So we need to have like good resolution to see the small details in these objects. And we all know that from the diffraction theory, because of the nature of light and waves, we have a limit in the resolution that we can achieve. And this limit usually is called this angular resolution is this lambda over d limits. So lambda is the wavelength which we observe, and d is the diameter, the aperture of your instrument. So if I take one example in the visible, if you have a small telescope of 10 centimeters, then you can have a resolution of 1 arcsecond, and that gives you maybe, for example, a nice detail on the moon or whatever. But if you would like to have the same resolution in the radio, for example, at 1 millimeter, which corresponds to 300 gigahertz, for the same resolution, you will need to have an instrument with an aperture of 200 meters. And if you want to go even better than this, then you will have to increase the diameter of your telescope even more. And the mission of ALMA is to get about the same resolution of the Hubble Space Telescope in space, that what the HST is doing in optical. So there's no magic there. The only solution is to do interferometry. And instead of building a huge telescope of 200 meters or even more, which would be very difficult technically to do because you will need a good surface accuracy and it will be very heavy and you need to move it if you want to look at different parts of the sky. Then the only way that the people have invented is to split this or to cut these big antennas into a lot of different small antennas like this and try to reconstruct the image from this. Of course, you see that this is, well, you see immediately that this is not the equivalent of a full field aperture, right? So you have a little price to pay for this, but in practice, it's much easier to do it this way. So the interferometry is a little bit tricky because what you see is not just directly an image, but what you see is the Fourier transform of the source intensity distribution. So maybe you remember when you go to the optician and then you make a test for eyes, then you have to say, okay, this is A, this is a C, this is a B. But if your opticians give you this, which will be the Fourier transform, I guess that maybe you will have a little bit problem to guess that this is the Fourier transform of E, right? Okay, so that's the problem, is that now we have to move into the Fourier space. And what the interferometer is measuring, it's what we call visibilities. And this comes with this mathematical equation here. And then the basic is that we do interference between two antennas. So you have a baseline with antenna 1 and antenna 2, and you are looking at the source. And what you measure basically is the electric field that is coming in each of these antenna. You see that the first antenna is seeing the wave coming from the source with a little delay here because of this extra geometrical path here. And this is exactly what is called the interference there. So one important thing is that these visibilities are complex quantities. So it means they have an amplitude and a phase. So it's not like the standard just an image where you have the intensity. No, we are moving this the image in the plane of the sky into complex numbers, amplitude and phase, and visibilities. And these visibilities, they all measured between pairs of antennas like this, and they are measured in what we call the UV plane. So you see the UV coordinates here. And this is just like imagine that you are from the source and you are looking down the antenna and you look the projection of this vector here, so the vector of the baseline. And you see the UV plane is this the projection of this vector here in the UV coordinates as seen from the source here. So now I just make the sketch for 2 antennas, but of course you have more antennas for an interferometer. And if you make a snapshot in the UV plane here, you see all these points here. That will be all the points that can be measured. This is an example for ALMA, for example. In 1 minute, you see all these couple of points. This is all the pairs of antenna here. And for each of these points, ALMA is measuring, or the interferometer is measuring an amplitude, a phase, and a weight for each of the channels in your correlator, and for each polarization, and this at each of the UV points here. But because the Earth is rotating, so the projection of your baseline will change, and you see that all these points start to move like this. And if you observe for 1 hour, you will get information on your source in all these UV points here. So what you can see here is that you cannot move the antenna as close to touch them. They will collide or they will crash. So there's a hole in the center here that you cannot get any measurements. So here in this hole, if you use an interferometer, you cannot measure the visibilities there. And the same, you cannot, well, there's maximum distance to put the antennas. I call this maximum baseline, Bmax here. And also, you are not measuring anything outside in the UV plane in distance more than this Bmax. So you have, and even in between, you also have, you see, you don't measure your visibilities. You don't get information everywhere here. You have some holes inside there. So you have an incomplete sampling. You are losing some information. And the price for this is that when you want to get back to your image after, you will not get maybe a perfect image. You will have to use a smart way to reconstruct your image to try to get the best of these observations. So if we're talking about the longest baselines, so this Bmax, this gives you basically the resolution, the angular resolution, the smallest details that we get, so the lambda over Bmax. And these central holes here, I will come back to this later, but this gives you the maximum scales of the structures that you can recover in your source, the lambda over Binging. Okay, so because it maybe is a little bit tricky to think in terms of visibilities, Fourier space, and things like this, so I will try to get an analogy. And what the Fourier transform is doing is to decompose your image into spatial frequencies. And the analogy I want to share with you here is about a Lego. Yeah, or maybe we all have played Lego when we were young. And actually, this will be your image in the sky. And that's what will do the Fourier transform, basically. So the Fourier transform, if you observe the amplitude, more or less is what how many pieces you will have of different size here to reconstruct your image. And the phase gives you the instruction how to mount the pieces together. So here you have small pieces, large, big pieces, and that's exactly what the sampling is done with the Fourier transform when you observe with an interferometer. The problem, of course, is you don't want to have just the pieces. You want to play with your beautiful Lego here. You want to rebuild your image of your astronomical objects. So you have to go the other way around when you have the pieces. So the problem, as I was saying, is that you don't have all the information. You are filtering some of the spatial frequencies. So we do not have all the Lego pieces to reconstruct our object. So now imagine that you have a compact configuration with all the antennas close to each other. So that would be equivalent to not being able to see the small pieces. So now you take this, then you don't have all the small pieces here. So you cannot see the very beautiful details in your spaceship here like this. So you are losing, or you have a limit of low resolution. So now if I move the antenna further apart, so that's what we call an extended configuration or long baselines. So that would be equivalent to lose the big piece in my Lego game here. So now I could see the small pieces, but then I will not be able to reconstruct the big wings or the big the extended structures in there. So this is what we call the problems of short spacings. So now I come back to the mathematical equations for those of you who like mathematics. And just now, if I go back to what is the meaning of these visibilities right at the center in this UV plane here. So the visibility at the point 0, 0, which we don't measure by construction. With an interferometer, you will never be able to measure this point here. And what is this? So if I put the U and V to 0 here in this equation, so the I, X, Y, this is the intensity distribution of your source. So this comes to 1 if I put 0, 0 here. So the meaning of this visibility at point 0, 0 is the integral or all the intensity on the sky. That means the total flux of the source. So again, with an interferometer, now you cannot measure this quantity. So it means you cannot measure the total flux of the source, okay? And also, it's not only the point at 0, 0, but you have everything to beam in. So you have no measurements in UV plane, sorry. You have no measurements inside the disk of radius beaming. So it means you are losing all the structures that are more extended than lambda over beaming, okay? So of course, that sometimes can be a problem, and it can lead to some potential artifacts when you want to reconstruct your image. But this is not, well, you have some ways to solve this. And for example, it's possible to get complementary data, for example, with a smaller array. Like in ALMA, you have two arrays, an array of a 12-meter antenna and an array of smaller 7 meters antenna that are much closer, which is called a compact array. Or you also can use single dish, also available at ALMA. And just to illustrate even more this, I just propose here to look at a model source where I put a ring and a point source here. And if you observe this with your interferometer in a compact configuration, and then you reconstruct your image from the visibilities, that you will get. So the point source will not be a point source anymore because you will have the maximum resolution of your lambda over Bmax. So this will be your beam. So this will be basically a Gaussian that reflects your resolution. And you see that now you don't really resolve the ring. You don't see the ring here because you don't have enough resolution to see the hole in the center. But now if I take longer baselines, so here I take the same observations, but I cut all the short baselines. I keep only the long baselines. You see that the resolution is getting a little bit better now. Okay. And then I start to see the hole here. But the trick is, now I take the same source models, but I add a very extended source here. If I observe this thing now with a compact configuration, I can retrieve more or less the model of the source, but you see some kind of artifacts around there, but at least you see that you recover the three sources. And now, if I do again the same trick that I remove all the short baselines, there's something dramatic that appears, that this extended source is completely disappeared now. You don't see it anymore because your interferometer is blind and you cannot see this one at all. Okay, so this is something that you have to keep in mind when you want to observe sources in the sky. You have to think if the interferometer can retrieve this or not. So that's why actually ALMA offers different array configurations. And actually it's like a dynamic instrument that is moving from a compact configuration with baselines of a few hundred meters. And then every now and then they're moving configuration, and then you can access different resolution. You are able to recover different size of your sources. That is what is called here. But Daniel will come in more detail on this. So just like to illustrate this compact configuration, here you have antennas. This is the antenna position. And you see they are further out. And then in extended configuration, you can move the antenna all the way to like 16 kilometers baselines. Okay. But in practice, when you prepare your proposal, we have this tool that we call let's call the ALMA observing tool. So you have to understand, or to at least to be aware of the limitation of interferometry, but the tool is built that, in fact, the PI is just need to input 3 key parameters, which are the angular resolution that you need, the largest scale in your image that you want to sample, and the sensitivity that you want to achieve. So basically, if you know that what you want to get here, and you input this, the observing tool is taking care of everything, and it will calculate which are the correct configuration that will match, and the correct observing time that will match this. So for you, in principle, it's transparent, but it's good to be aware of the limitations. Okay, and then the next thing is ALMA is at a very good site at 5,000 meters high in Chile. It's very high, it's a very good site, but they still have a little bit of atmosphere. And the effect of atmosphere can get some problems in the millimeter sub-millimeter window. And I will just briefly introduce this. So this is the transmission of the atmosphere in the millimeter sub-millimeter window between okay, let's say around 100 gigahertz to 1000 gigahertz. So the ALMA bands are shown in green here, and I guess this is the band 1 that was recently added here. So if you observe at low frequency, you see that the atmosphere always is almost transparent. You almost have 100% transmission. That's almost no problem, okay? But when you go to higher and higher frequencies, all the curves with the different colors here, they show you the weather condition, basically. So the blue is the best, and the yellow-orange here is the worst observing conditions. And it's basically the amount of water vapor in the atmosphere. ALMA is very sensitive to the water vapor. That is what is causing this very big absorption in the atmosphere. So you cannot, for example, here, you cannot observe at all because of the water lines here. So the best observing conditions, you still have it's still possible to observe even in band, I guess this is band 10, band 9, band 8 here, sorry. Still possible to observe, but it's not all the time. You only have a small fraction of the time when you can really observe here, when you have a decent atmospheric transmission. And when the weather is very bad, then it's basically you are not able to see anything at this high frequency here. So when you, for example, if you want to observe at the highest frequencies here in ALMA band 910, first you need extremely good weather. So it means you need to observe in the best conditions, which are not all the here at ALMA. So you have to be careful where is your source, in which coordinate, which LST, and then to make sure that during that time the weather conditions usually are okay. Maybe it's good to be aware that you have a lot of these atmospheric lines, maybe that can perturb your observations also. So maybe if you want to observe a spectral line around one of these, maybe it's you have to be a little bit careful. And another thing, when you observe high frequency, that the field of view is getting smaller and smaller. So maybe you have to go for mosaicing and things like this, so everything maybe is a little bit more complicated. And the final thing I wanted to say is about this. I didn't say too much about the phase until now, but I say that we need to measure this amplitude and also the phase to reconstruct your image. So what we want is, again, to move from the visibilities back to the image. So that's the invert Fourier transform. So we need to reassemble all these pieces. And if for some reason you have like water clouds in the atmosphere, or like in optical you say bad seeing, the equivalent of bad seeing, then you will introduce some phase error in your observations, and that will be equivalent to give wrong information on how to mount the pieces. So if you have a small phase error, then instead of putting your pieces here, maybe it will move, and then you think that you will have to put here, but it's a mistake of the observation. So maybe you will reassemble not the correct way. But in principle, you have some remedy of this. So of course, ALMA is doing a good phase calibration. And depending on your source, also you can do self-calibration. So if you have a relatively good model of your source, then you can correct the phase to reassemble this correctly. Okay. So just in summary, actually interferometry is very simple. It's as simple as a Lego game, as I show you. But what is important is that the interferometer is a filter and is only sampling few special frequencies. So you have a trade between the small and extended structures of your source. An interferometer will always give you an incomplete sampling, so you will always lose some information. But sometimes it has an impact on your science goals. If you want to observe extended structures, for example, you have to be careful. But sometimes it doesn't matter. If you want to observe point source, you see that the compact or extended configuration are equal for those sources. So you have to be a little bit aware that the Earth atmosphere also is altering your observations and alters your ability to reconstruct images. But usually ALMA is delivering very high quality data. So in principle, you get what you ask in the observing tool. So ALMA is always giving very good quality data.